Hello friends, welcome to CEC Live Lectures. Dear friends, with our ongoing series on solid state physics, in our previous session we discussed a lot under the series that is solid state physics. This is the second lecture in this series, and today also we are going to talk in depth on the topic. Friends, for this discussion we have with us in our studios the young and dynamic professor. We have with us Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor in YMCA, University of Science and Technology. Dr. Bansal has immense experience and she is contributing a lot in the area of academics. She believes in giving most of her experiences, her knowledge to the students, and therefore through this live platform she always believes to give her utmost experiences or utmost knowledge to the students. Friends, if you want to ask questions from Dr. Sonia Bansal on today's topic, then do call us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. All dear friends are requested to call in the last 10 minutes of the lecture so that first of all you get in-depth knowledge on today's topic, and afterwards we promise to give answers to your questions through Dr. Sonia Bansal. So friends, let's welcome our guest Dr. Bansal and let's try to get in-depth knowledge on today's topic. Hello ma'am, welcome to the lecture.
Thank you Geetika. Last time we discussed about the solid state physics. In the solid state physics, we discussed about the crystal structure. The various crystal structures we define. We define the Bravais lattice, and we define the packing factors. We define the density of the different crystal structures. Now we will discussing about the Miller indices, which represent the address of a plane. Means if we define any plane, then we have to give some name of that plane. That plane name is defined by the Miller indices and its value is HKL. Now how we calculate the Miller indices? As we have the intercepts, then we take the intercepts, take the reciprocal of that, then we take the highest denominator, and on the basis of that we calculate the Miller indices, and we have the HKL values, means the address of a particular plane. Now again we start with the Miller indices. What is the Miller indices? Defined as the reciprocal of the intercept made by the plane on the three axes. How we calculate? There are three steps to calculate the Miller indices. Now, in the first step, we take the intercepts. Means we determine the intercepts of the plane along the axis x, y, z in terms of the lattice constant a, b, c. Means corresponding to x we calculate the a, corresponding to y we take the intercept b, corresponding to z we take the intercept c. After that we determine the reciprocals of these numbers. After calculating that, we find the least common denominator, or we can say LCD, and multiply each by this LCD. Now in the step 4, the result is written in the parenthesis, and we write this value in the form of HKL. That denotes the Miller indices of that particular plane or the address of that plane. Now here we have an example. Here we have a cube and we have the different intercept at the different axes. First we start with this x-axis. Now at x-axis the intercept is 2, 0, 0, and at the y-axis the intercept is 0, 3, 0, and at the z-axis intercept is 0, 0, 1. Now first we take all the intercept of the three axes, means we take 2, 3, 1. Here we have x-axis, we have 2, and at y-axis we have 3, and at z-axis we have 1. Then we can write it as all the intercept of the axis, that is 2, 3, 1. Now we take the reciprocal, which is equal to 1 by 2, 1 by 3 and 1 by 1, or we can write it as 1. Now convert the smallest integers in the same ratio, then we will calculate it as 3 to 6, and we just put it in the parenthesis, and now 3 is the H, 2 is the K, and C is the L. It means HKL value is 3 to 6, or the address of this plane is 3 to 6, and it is also known as the Miller indices of that plane is 3 to 6. Now plane, we are having the ABC intercept, and here we just can see from the diagram that at the x-axis we have the intercept at the 2 unit. As previously we defined, this is 1, this is the second, and all considered as a unity. Now at y-axis the 3 units we have, and at the z-axis we have 2 units. In this manner we have the 3 intercept, and on the basis of that we calculate the Miller indices. Now Miller indices for the plane, as we discussed, 2, 3, 2, and we can calculate the reciprocal 1 by 2, 1 by 3 and 1 by 2. Previously we have taken 1, now here we have the intercept 2. That's why we have written as 1 by 2. The least common denominator now will be the 6. Then multiply each reciprocal by it, and we can get the 3, 2, 3. And now finally we get the Miller indices in the form of 3, 2, 3. 3 is the H value, 2 is the K, and 3 is the L value. It means for the intercept 2, 3, 2, we have the HKL values 3, 2, 3. Again, there are some features to express the Miller indices. Apart from that, we define that if the plane is parallel, then we consider it as a infinite. Means intercept will be infinite if any plane is parallel. If then it is infinite, then the Miller index of that particular infinite plane will be 0. And a plane passing through the origin is defined in terms of parallel plane having non-zero intercepts. Means we will not consider it as a 0, it will be the non-zero intercepts. All equally spaced parallel planes have the same Miller indices. It means 1, 1, 1, 2, 2, 2, 3, 3, 3 planes are having the same Miller indices. The Miller indices do not only define a particular plane but also a set of parallel planes. Thus, the planes whose intercepts are 1, 1, 1, 2, 2, 2, minus 3, minus 3, minus 3 are all represented by the set of same Miller indices. Now we take another example. Here we take the axis which is in the negative direction, then calculate the Miller indices for the plane with the intercept 3a, minus 3b and 4c along the crystallographic axis. Then we have the intercept. For the x-axis it is 2, for the y-axis it is minus 3, and for the z-axis it is 4c, then we consider it as a 4. Now we take the intercept as 2, minus 3 and 4 along the 3 axis. Now we take the reciprocal of that, it will be 1 by 2, minus 1 by 3 and minus 1 by 4. Now we take the least common denominator is 12, then multiplying each reciprocal by the LCD, then we have the values 6, minus 4 and 3. It means HKL values are 6, minus 4 and 3, but we write it as 4, not in minus sign, but we put a bar on it. Now the Miller indices for the plane 2a minus 3 or phi c is 6, 4 bar and 3. For the minus sign, you remember that for the minus sign we always use bar for the Miller indices. Now we take the intercept, we consider the infinite plane. Let us consider this. Just we take the this cube, then we find out the intercepts at 1, infinite and infinite. Means this plane we are considering, which is representing as a red, then at x-axis it has an intercept 1, and along the x-axis and at the x-axis it has a intercept 1. Along the y-axis and along the z-axis, the intercept are infinite. Now we have the plane 1, 0, 0, then family will be the 1, 0, 0. All the intercept belongs to this family, we have the same plane address. The purpose of using the reciprocal of the intercept and not intercept themselves in the Miller indices become clear that infinity are removed. Now if you consider this intercept, means here x-axis intercept at 1, y at 1 and z at infinite. Now the plane will be 1, 1, 0, and this family represent the 6 planes which are parallel to this particular indices. Now we consider this triangle, then intercept of this all axes cut at intercept 1, 1, 1, then we define the plane 1 by 1, 1 by 1, or we can write it as 1, 1, 1, then family will be 1, one H, one K and one L, and we have the 8 planes in this family. Now consider this intercept. Here we are seeing that the shaded portion cut the axis at intercepts are A, not, not. Then if we calculate the Miller indices of this, then we will have 1, 0, 0. Similarly, we consider the another plane. If the intercept are A infinite, means we are having the fractional intercept 1, 1 infinite, then we have the Miller indices 1, 1, 0. The shape of the plane is in this manner. Now, this is a triangle, all the intercept cut at A, then fractional intercepts are 1, 1, 1, then we can calculate the Miller indices as 1, 1, 1. Now, intercepts 1 by 2 A and infinite. And then the fractional we have 1 by 2, 1 and infinite. Then Miller indices will be 2, 1, 0. Next plane is, here in this cube we have the different planes, means at 1, 0, 0, at 0, 1, 0 and 0, 0, 1. At all these planes we define the Miller indices for 1, 0, 0, for 0, 1, 1 and this plane is 0, 0, 1. Now we have the crystal planes. The planes can also have the negative intercept, as I already discussed. Then we have this plane 1 minus 1 by 2 and 1. Then we have the HKL value for this is equal to 1 minus 2, 1 and that will be denoted by 1, 2 bar 1. What is the family of the planes? Means what is the HKL values of that a particular crystal planes. Planes having the similar indices planes having the similar indices are equivalent, then the faces of the cube 1, 0, 0, 0, 1, 0 and 0, 0, 1. This is termed as a family of the planes and denoted as in the parenthesis 1, 0, 0, which includes all the 1, 0, 0 combinations. All the 1, 0, 0 combinations includes the negative indices also. Means all the minus sign we can consider in this combination also. Some other equivalent planes we have, just see here. This is the family of 1, 0, 0 and this is a family of this plane is defined the 0, 1, 0 and this define the 0, 0, 1 and here we define the 1, 1, 0, 1, 0, 1 plane and this is 0, 1, 1 plane. All depend upon the intercept at the different 3 axes. In this plane we have the 1, 1, 1. Here we have the negative, means origin is shifted from blue to red in this circle and here we see that this is the positive plane and this is the negative, means x-axis at the negative sign and here the y-axis is the negative indices. Means here this is the index 100, 110 and 111. And we have the cubic lattice for this family. For 100 plane, we have the different planes, means 100, 1 bar 00, 010, 0 minus 1, 0. For that we write it as 0, 1 bar 0, 001 and 00 bar. Then we have the 3 into 6 means we have 6 numbers. Now for the index 110, how many planes we have? We define all the positive and negative planes. Means we are having the 110 first plane, the second plane for the negative x, then we have 1 bar 10. Now here the negative y, then we can write it as 1 bar 10, then 1 bar all the planes x or y in the negative direction. Now 101, 1 bar 01, 10, 1 bar, and these are all the family of 110 index. Now the third one is 111. In this plane we define 3 x's, then here 1 bar for the negative x, means the x value is negative. Here the y value is negative, here we see that the z value is negative. Now we consider the two negative x's, means x minus y and z is positive. That's why we have written 1 bar and 1. And in the next we have y positive axis and x and z are negative axis. And in the next one we have x is positive and y and z is negative. And the last one we have all the bars, means all the negative values we are considers. Then 4 into 2 is equal to 8, the negatives opposite directions. 2 is defined as the negatives define the opposite directions. We can write it by using the symbol, bigger parenthesis, and by using this, or we can write the Miller indices in this parenthesis also, means particular direction and particular families we will define by the these parentheses. Next is Miller indices for the plane. Here we again define one of the example which define the Miller indices. Miller indices for a plane is not intuitive as that for the direction, and the special care must be taken for understanding them. Means here we just see one cube which has a unit value. Now we take the intercept here, this is a 1 unit. Now we consider the point A. Here this is a 1 unit and this is the second unit. It means that x axis it has a 2 unit. And similarly here for the, if we consider the y axis or we consider the B which is having a 3 unit, 1 for this cube and 2 are more defined here, then we have the 3 unit cut unit. Now for the y we have for the z we have the single unit cut. Then intercept we have 2, 3 and 1. Now we take the reciprocal again, take the ratio and enclose in the parenthesis. Parenthesis does not represent the plane but a set of parallel planes passing through the lattice points. It means we define all the planes under this are denoted by the 3 to 6. Set of planes should not be confused with the family of the planes, which we shall consider in the next slide. Now, why do need Miller indices? Say for the planes, we cannot just use the intercept to designate the planes. Firstly, we define the intercept. If we define any plane, we use the intercept. But is it possible to define any plane by the intercepts? We require the Miller indices. We require some addresses of that particular plane, and we define that particular indices for the particular family. Thus, we see the Miller indices does the following things. It avoids infinites in the indices. Intercept of 1 infinite, it becomes 100 index. Means in Miller indices we never define the infinite. about dimension numbers, means instead we have multiples of lattice parameters along the ABC direction. This implies that 1A could be any value 10.2 angstrom, or 2B can have the value 8.2 angstrom. As we done previously, we will continue to call planes in the lower dimensions, like we can say it in the 2D as planes through they are actually lines in the 2 dimensions. Now, what is the concept of family in the Miller indices? A set of planes. We are defining not the single plane, but we define the set of plane in the Miller indices. Then a set of planes related to symmetric operations of the lattice of a crystal is called a family of plane. The translation symmetric operation is excluded in this term. Then translation symmetry is included in the definition of the plane itself. Means if we define a single plane, then we define the translation vector, but here we are taking the family of the planes. All the points which one should keep in mind while dealing with the direction to get the members of the families. It means we have to note that we are just working in the positive direction, or we are having the negative axis also. Now we again take the one example. The intercept can be defined as x is equal to 2a, y intercept is 3 by 2b, z is equal to c. Now we first find out the form of set. It will be x by a, y by b and z by c. Intercept we take from this equation, we have 2, 3 by 2 and it is c, then we take it as a 1. Then the inverted we have 1 by 2, 2 by 3 and 1. And finally multiplying by the common factor denominator, which is 6, then we obtain the Miller indices 3, 4 and 6. This explains the Miller indices of the plane 2a, 3 by 2b and c. Now this exercise we can be done by x is equal to 2a, y is equal to 3b and z is equal to 6c. Again we take the reciprocal of that, it will be 1 by 2, 1 by 3, 1 by 6. Then we take the 6 denominator. Here we have 3, the value 2, here 1. It means the Miller indices for this plane where it intercept at 2a, 3b and 6c will be 3, 2, 1. As the Miller indices for a plane line 100 implies a infinite parallel set of planes. Now points about the planes and the directions. Direction corresponding to a particular family means all will be in the positive and negative direction. Unknown general planes will be defined as HKL. Corresponding family defined by this parenthesis also. Double digit indices should be separated by commas or spaces. Here we can write HKL values in this manner, means we can write the comma or we can write the single values. Here we see the 12, 22 and 3 are the Miller indices. We can write it as 12, 22 and 3. In cubic lattice crystal, the HKL planes is perpendicular to the HKL direction. Means specific plane perpendicular to the specific direction. Here this defined is. However, this cannot be generalized for all the crystal lattice. We have some example here. The interplane spacing can be computed knowing the Miller indices for the HKL values. Means we are defining the planes, we define the Miller indices, then how we define the interspacing between these two planes. Then interplanar spacing can be computed knowing the Miller indices of the HKL value, then kind of lattice involved in it. The formula to be used to depend upon the kind of lattice, and the formula for the cubic lattice is given below. Here this is the formula, which is D spacing between the two Miller indices or spacing between the two planes defined by A divided by root of S square plus K square plus L square. Then interplane spacing DHKL and the cubic in a cubic crystal. Means the Miller indices defined by HKL, the interplanar spacing defined by the DHKL values, and the formula we will calculate by using D is equal to A by root of S square plus K square plus L square. What does the symbol 111 means and represent? The symbol 11 represents the Miller indices for an infinite set of parallel planes with the intercept 111 along the three crystallographic axes, or we take the unit lattice parameters along these crystallographic axes which passing through the lattice points. These are the intercepts for that particular point. The 111 is the Miller indices for a plane. It is usually for a infinite set of parallel planes with a specific D spacing. Hence, 1 0 plane is no different from the minus 1 0 0 planes. The set consists of the plane related to by the translational symmetry. However, the outward normal of these two planes are different. Sometimes it is used for the specific plane, sometimes we define it as a single plane also. Now, are these members of the family of 1 0 0 planes? Means 1 0 0 0 1 1 0 0 1 minus 1 0 0 0 minus 1 0 are all belongs to the 1 0 0. This is the meaningless because without specifying the symmetry of the crystal, the above is true. If one is referring to a crystal with a symmetry, the family is symmetric related to the set, then we can say that if we define a single plane, then we define by the 1 0 0 or by the different values.
With this note, thank you ma'am, thank you so very much for giving us a session on solid state physics, and dear friends, we would be meeting after a short break and would be discussing more under the series as well as under the topic. Hello friends, welcome back to this session where we are discussing on solid state physics. We believe that you have learned a lot in the previous session, and in this session also we are going to give you most of the knowledge. Friends, if you want to ask questions from Dr. Sonia Bansal on today's topic, then do call us at our toll-free number. Our toll-free number is 1-800-110-430. So I would like to request Dr. Sonia Bansal to continue further and give us more and more information on solid state physics. Hello, ma'am. Welcome to the lecture.
Thank you. We are discussing about the Miller indices. We are defining the different planes in the Miller indices. Then here again we consider the parallel planes. This plane passing from the origin, then intercept we have infinite, 0, infinite, and then this plane is also parallel to this plane which is having the indices 0, 1, 0. Now plane is 0, infinite and 0, then intercept is 0, infinite, 0 and infinite, but the plane will be 0, infinite and 0. Similarly here we have the different planes at 0, minus 1, 0. Then we can write it as 1, 1 bar 0 and 1, 1 bar 0. Now plane passing through the origin, we have the different intercepts. Intercept will be 0, 0, infinite. The plane will be infinite, infinite, 0. We want to avoid the infinities in the Miller indices. In such cases, the plane is translated by the unit distance along the non-zero axis and the Miller indices are computed. Now here we define the different Miller indices. What about the plane passing through the fractional lattice spacing? Here we are having the different planes 0, 1, 0, this is 0, 2, 0 and this is 0, 1, 0. Intercept will be infinite, 1 by 2 and infinite. The plane will be 0, 2 and 0. In a simple cubic lattice, this plane will not pass through the lattice point, but then the lattice plane have to pass through the lattice points. Why do we consider such planes? We will take this plane as this is the parallel to the 0, 1, 1. This is the interspacing between the two planes that we will discuss later. Here we show that the two planes are having these planes are having the different at the different distances. Means we have 0, 1, 1 plane, 0, 1, 1 plane. They are separated at a particular distance that we will calculate it by this vector d. 0, 1, 1 cubic lattice, the plane will be defined by the A, 0, 1 and 0. The two planes 0, 1, 0, 0, 1, 0 are separated by a distance A. Similarly here we have the different planes 0, 2, 0, 0, 2, 0 and they are separated by the distance A by 2. Now, why talk about the 0, 2, 0 planes? As we already discussed, isn't this the same as 1, 0, 1, 0 planes as we factor out common factors in the Miller indices? Yes, totally yes. This in the Miller indices we usually factor out the common factors here. Suppose we consider a simple cubic system and we have the alternate 0, 2, 0 planes which have not any atoms in them. Then the planes will not pass through the lattice points as the plane are usually required to do that. Sometimes it is added separately. Later then we talk about the X-ray diffraction. Then second order reflection from 0, 1, 0 planes are often considered as a first order reflection from the 0, 2, 0 planes. This is one of the reason we need to consider 0, 2, 0. For that matter, 2, 2, 2, 2 multiply 1, 1, 1, and similarly 3, 3, 3 multiply by 3, and 2, 2, 0. These are the kind of planes which are parallel to this plane. Similarly, we will also talk about the 1 by 2, 1, 0, 0 kind of direction, where 1 by 2 in front is left out for the length of the vectors given by the direction. That is, we are not only concerned about the direction, but we are also concerned about the length represented by the vector also. We talk about the spacing between the two planes. How we calculate the spacing between the two planes, that is known as the interplanar spacing of the Miller indices. For this, we consider the three mutually perpendicular coordinates along OX, OY, this is OX, OY and OZ. Assume that the HKL parallel to plane passing through the origin. We consider it one plane at the origin whose intercepts are A by H, B by K and C by L on the three axes at A, B, C respectively. This plane A by H, B by K and C by L we are considering at the origin. Now OP, this is the OP, this is the one plane which is the origin, and next plane is defined by CAB, which is parallel to the origin, and we will calculate the spacing between the plane which is at the origin and the plane which is at the distance P. Means we are calculating the OP. OP define the interplanar spacing between the two planes. One plane is here, second plane is here. The interplanar spacing between these two is defined by OP. That is defined by DHKL. HKL for the Miller indices, D is the spacing between the planes. The interplanar spacing by normal, the plane draw from the origin. We draw the origin and then make an angle alpha for the x-axis, beta for the y-axis and gamma for the z-axis. It means this perpendicular cuts the plane along the three angles which is alpha, beta, gamma along x, y and z axis respectively. Then we define OA. What is OA? This OA we consider the right angle triangle. OPA, we can calculate OA is equal to A by H. This point cut at A by H. OB cut at B by K, on OC cut at C by L. These are the intercept. Now from the triangle OPA we have cos alpha as it is along the x-axis. Then we calculate the cos alpha, here we mentioned, which is equal to OP by OA. Then using the right angle triangle Pythagoras theorem, OP already defined, which is DHKL. Here we put DHKL and OA as the intercept, which is A by H. Now put this value here, the value of OP and value of OA. Similarly for the other triangles, means for the triangle OPB, this is also a right angle triangle, and then the triangle OPC. From different triangles, we will calculate the value of cos alpha, cos beta and cos gamma. For the cos beta is equal to OP by OB, we can write it as DHKL divided by BK. From triangle OPC, it is cos alpha gamma is equal to OP by OC, which is equal to DHKL by C by L. Now from the rectangular coordinate system, using the direction cosine, we can define cos square alpha plus cos square beta plus cos square gamma is equal to 1. Now substituting the values of cos alpha, cos beta and cos gamma in the equation 1, we get d square HKL h square by a square plus k square by b square plus l square by c square is equal to 1. Then we define DHKL is equal to 1 by, we take the root of all these value and we take in the inverse form and we calculate the root of that. This is in general formula and is applicable to primitive lattice of the orthorhombic, tetragonal and cubic system. For the orthorhombic system, we know that A is not equal to B is not equal to C. Then the HKL value for this is DHKL, interplanar spacing, is defined by square by a square plus k square by b square plus l square by c square, as the three axes are equal. For tetragonal system, a is equal to b is not equal to c, then we define DHKL is equal to 1 by s square plus k square by a square plus l square by c square. These values can be have the different values. A and B defined here is equal to 2.42 angstrom and C defined by the 1.74 angstrom. And then D is equal to 101 is equal to 1.41 angstrom. For the cubic system, we define A is equal to B is equal to C. Then D we define, if we have the A, B, C equal, then we can remove from here and we put it value here, it will become A square. Now A square can take A upper side, and finally the cubic system have the interpillar spacing which is equal to A divided by root of s square plus k square plus l square. If we put the value of A is equal to 2 angstrom, the value of this plane 1 1 1, but interspacing between these plane will be 2 root of 3 angstrom. If the value of A is equal to 421 angstrom, the spacing of D32 plane will be 1.01 angstrom. In this manner, we can calculate the different values of the different planes, interspacing distance between the different planes for the different families. Now here we see that the ratio of the interplanar spacing of these plane for the D00, D11, D11 is defined as 1 by root 2, 1 by root 3. The next example is we calculate for the D100, its value is A by 2, D110 value is A root 2 for the BCC structure, for the BCC cluster structure. We define interspacing between the planes for the 111, it will be A by 2 root 3. If we take the ratio of these three, we have 1 root 2, 1 by root 3. For the BCC, for the different planes, and similarly we will define for the, here the value of plane will be changed, it will be 100, then it will be A by root 2, A 2 root 3, then the ratio will be 1 by 2, 2 by root 3. Now we determine the Miller indices of a plane which is parallel to the axis and cut the intercept at 2 and 1 by 2 respectively along the y and z axis. Then we can calculate the intercept, as here the x-axis is not defined, we consider the x-axis is parallel. So we take infinite. Intercept will be infinite, 2b and 1 by 2c. Then we take the division by unit translation, it will be infinite, it will be 2 and 1 by 2. Now take the reciprocal, 1 by alpha, 1 by a, 1 by 2 and 2. The cleaning fraction we have 0, 1, 4. Now Miller indices will be 0, 1, 4. And the next example, Miller indices of a plane treating by the intercept 2a, 3a, 4 on the coordinate axis of the orthorhombic crystal, which is A ratio B ratio C, will be 4, 3, 2. Then the unit translation are A is equal to 4, B is equal to 3 and C is equal to 2. The following same procedure we have the intercept 2, 3, 4. From the previous we take it as 2, 3, 4. Now division 1 by 2, 3 by 3 and 4 by 2 we take 1. Reciprocal 2, 1, 1 by 2. After cleaning the fraction we have 4, 2, 1. Now Miller indices for this plane 2, 3, 4 will be 4, 2, 1. Bragg's law. What is Bragg's law? We define the lattice of a plane. We define the distance between the two planes or the spacing between the two planes. Then why we require the spacing between the two planes? The plane in lattice and the Bragg's law. We are interested basically in the planes in the crystal lattice in the context of X-ray diffraction because of the Bragg's law, which is equal to 2d sin theta is equal to n lambda, or we can call it as n lambda is equal to 2d sin theta. What is n? N is defined as an integer, lambda is a wavelength, 2 is a numeric value, and what is d? D is the interplanar spacing, or we can say distance between the adjacent planes in the lattice. Theta is the angle of X-ray beam which is incident on the crystal. Here we see in the diagram that X-ray beam is falling upon a lattice which is parallelly, the planes are parallelly spaced. The light from the X-ray fall upon the crystal lattice, or we can say at a crystal point, and from here it is reflected. And similarly here the light is falling at different angles and it is reflecting from the lattice points. Now the light of the wavelength lambda falling upon it, and it is incident at an angle theta, and it will reflected towards the another direction, and here we are having the different planes and light is falling at the different lattice points. Now we will calculate that Bragg's law tells us the condition that must met for the reflecting X-ray waves to be in phase with each other, and they will constructively form the interference. If these conditions are not met, then we get the destructive interference, which reduces the reflected intensity and which will be 0. Means by using this we are calculating the constructive interference and destructive interference for the maximum or the minimum light respectively. In 1915, Bragg defined the Bragg's law to define the various planes light for to define the properties of X-rays. Here we define the X-rays by using a plane. Here we consider the two planes. They are separated with a distance d. X-ray fall upon the lattice point of one plane, and from here it is reflected at an angle theta. Again the next X-ray fall upon a lattice point B, and from here it is reflected. Now here we have different points A, C, B. A, B, C are the points from where. Now we draw the AZ perpendicular on the X-ray, and here we define the ZC perpendicular on the second ray. The Bragg's law can be derived using the simple geometry by considering the distances travelled by two parallel X-ray reflecting from the adjacent planes. The X-ray hitting the lower plane must travel the extra distance as compared to the light falling upon the upper plane. Then the extra path is A, B, B, C. To remain in the phase with the X-ray, this distance must be multiple of the wavelength. Thus, we define it as n lambda here, n lambda, part difference will be n lambda, which is equal to A, B plus B, C, or we can write it as 2AB. These difference are same. Since the two triangles are identical, so we write AB in the 2 times. Apart from the BC, we can write it as AB. The distance AB can be expressed in terms of interplanar spacing, which is D, and incident angle is theta, because D is the right angle at ZAB, which is shown in the right hand side. Here this is the theta. Now we define the sin theta, which is equal to AB by D. We can write AB is equal to D sin theta. Now we put the value of AB in the previous equation, and lambda, part difference will be D sin theta, means the Bragg's law will be 2d sin theta is equal to n lambda. D and sin theta are inversely proportional or reciprocal to each other. This means the smaller value of the D diffract at higher angle. This is important of the high angle data. Now, by using the Bragg's law, we solve the one example. Determine the angle through which the X-ray of the wavelength 0.440 angstrom will be reflected from the cube face of the rock salt crystal, whose interplanar spacing is defined by the value D is equal to 2.814 angstrom. By using, now we know that lambda is equal to 0.440 angstrom, D is equal to 2.814. Then we know the formula 2d sin theta is equal to n lambda. We can write it as theta is equal to sin inverse n lambda by 2d. For the first order, n will be the 1. Then theta 1 is equal to sin inverse. We put these values in this equation and we get the sin 0.0782 and the value is 4 degree 29 minute. To second order, n will be changed from 1 to 2. Then we get the angle 8 degree 59 dash. Third order, we again put the n is equal to 3. Then we can get the 13 degree and 34. Now here see, the angle is increasing from first order to second order to third order reflection. The next example, we will determine the wavelength also of the diffracting beam, where the X-ray having the wavelength of the range of 0.2 angstrom to 1 angstrom incident on the angle of 9 degree with the cube face of the rock salt crystal of the interplanar spacing, which is 2.814 angstrom. The value of n1 for the order 1, we define 1 lambda 1 is equal to 2 into the value, as the value is 2d sin theta. The 2, this is the value of d, sin and theta is the 9 degree. The lambda for the first order will comes out 0.8804 angstrom. Now for n is equal to 2, the lambda will be 0.04402. For n is equal to 3, the value is 0.29. Now here we see that for n is equal to 5, the value is 0.1760. As the order increases, the wavelength decreases, which is must be less than 0.2 angstrom, which shows the wavelength of the X-ray are in this manner and this is decreasing. We define the various experiment of X-ray diffraction method. To define the X-ray diffraction, there are the different methods. To satisfy the Bragg's law, it is necessary to vary either the angle of inclination of the specimen to the beam or the wavelength of the radiation. The three standard methods of the X-ray crystallography are used to define the Bragg's law. First is the Liu method, second is the rotating crystal method, third is the powder method. Liu method, which defines the stationary single crystal, is irradiated by range of X-ray wavelength. In the rotating crystal method, we have a single crystal specimen is rotated in the beam of monochromatic X-rays. In the powder method, we have the polycrystalline powder, or we have the microcrystals as a specimen to keep stationary in a beam of monochromatic radiations. Of these techniques, Liu method is used only for non-crystal orientation measurement. And we define the three X-ray diffraction, means Liu method, rotating crystal method and powder method. These three methods define the X-ray diffraction, and we define the crystal structure of a particular crystal by using this method, and moreover by using this we define the symmetry of the crystal. The one of the application of this method, Liu method, is by this method we can find out the symmetry of particular crystal through which the X-ray will pass, and we can calculate that the X-ray can be diffracted, means diffraction pattern can be obtained by the X-rays, and by rotating crystal methods we can get the diffraction pattern of the rotating crystal also. In the powder method we can take the microcrystals, and we can calculate the different diffractions by using the microcrystals. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us a productive session on solid state physics. Dear friends, we believe that your feedbacks are very, very important for us. So do write to us at info.cec@nic.in. This is the ID where you can contact us. You can give your feedbacks, your suggestions, as well as you can post your questions over there, and we'll try to give answers to your questions when next time Dr. Sonia Bansal visits our studio. Dear friends, all the lectures pertaining to the series are there on the YouTube. Apart from this lecture, which we are going to upload on YouTube very soon, you can see number of lectures on varied subjects on our YouTube channel. Our YouTube channel could be viewed easily on www.youtube.com/CEC-UGC. Friends, we would be meeting again very soon and would be discussing on more under the series solid state physics. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.